Hey there. A while ago, maybe a couple of years at this point, I did a video or two on solving boundary value problems, differential equations with boundary value problems via the shooting method. And shortly thereafter, in the comments, I received a question on how would you handle eigenvalue problems. So not only do you have to solve the differential equation, but you have to impose your boundary conditions and get the eigenvalues and all the eigenfunctions from that. So in the comments I did answer, but I don't think I did the best of job in justifying how I handled the boundary conditions, especially the first derivative. And because a couple of people have been asking recently about boundary value and eigenvalue problems, I thought I would do a quick video on it. So we're going to solve a very simple problem that can actually be done by hand from quantum mechanics. Don't let that scare you. It's pretty basic. It's just a solution to a differential equation. And we're going to work out what the energy levels are for this particle in a box problem that's very typical. You probably even do it in like sophomore year in a college physics course. So we will do that numerically here via the shooting method. And yeah, let's just jump into it. So we're going to look at a problem from quantum mechanics that's commonly referred to as the particle in a box or the infinite square well problem. So what we have here is basically a particle confined between two points. So in terms of energy, we're going to have the potential energy be 0 for x between 0 and L. And for anything outside this range, the potential energy will be infinite. And since a particle can't have infinite energy, it's going to be trapped in between these 2 points, x is equal to 0, x equal to L. So classically, the particle can have any type of kinetic energy it wants, just as long, and its only constraint is basically to stay in between these 2 points. So here is the potential energy just kind of written out in mathematical form. And for the quantum mechanical problem, we're going to solve the time-independent Schrodinger equation kind of written here. So some constants, h bar squared minus h bar squared divided by 2m, and we're going to take we're going to take this to be an electron, so this is going to be the mass of the electron. The second derivative of our wave function, which is what we want to solve for. This term plus the potential energy times the wave function is equal to some constant E, which is an energy, times, again, the wave function. And you notice that this is an eigenvalue problem. We have some sort of linear operator here, so this h bar squared, d squared, psi dx squared, plus the potential energy operating on psi, gives us back our wave function times a constant. So this is an eigenvalue problem. And obviously we can rearrange it so that it reads like this. So this is just all combining all the terms to one side. And before I go on, for the actual calculations, I am going to use SI units. So the mass is going to be in kilograms, the distances are in meters, and so on. It's going to work for this problem, but in general, you would probably want to rescale things or choose units such that everything is on order unity. It just so happens that you don't really have to do it here. So for the sake of simplicity, I'm just going to keep everything in SI units. So for this simple potential, this equation here can be solved analytically easily enough. Since the particle cannot have any energy outside of this range 0 to L, the wave function is 0. And so we only have to solve the equation for inside the well, but the potential energy inside the well here is 0. So this equation is going to simplify somewhat. So let me rewrite that with the potential energy term taken into account. So okay, here we go. V is equal to 0 inside the well. So our equation simplifies to this. And again, because the particle cannot have infinite energy, we know our boundary conditions at x is equal to 0 and x is equal to L. That's just the wave function itself is equal to 0. So we have a boundary value problem and an eigenvalue problem here. So again, this can be solved simply enough. So let's just do that. And before we actually do that, I should make one note about this. If we integrate the square of the wave function over all of space, which for this problem is just going to be basically between 0 and L, since the wave function is 0 outside of the well, if we integrate the square of that wave function, it is equal to 1. So the, how do I want to say this? The square of the wave function integrated between 2 points in space is basically going to give you the probability of being within that region. And since we're integrating over all of space, the probability of the particle is somewhere is 1. So we are going to take advantage of that eventually to get one of our constants of integration. So where was I? Boundary conditions. Here, we're going to just substitute in this just to simplify our algebra a little bit. So k squared is equal to 2m E, our energy, over h bar squared. So our equation is this, and this has a very simple solution. Psi is equal to a, some unknown constant of integration, sine kx, plus b, again another unknown constant of integration, cosine of kx. So our left-hand side boundary condition, psi at x is equal to 0 is equal to 0. That implies that, let me fix a typo here. Where was it? Boundary conditions implies, and I saw something else that was a little fishy. Cosine of 0 is equal to 1. So how does that look? Yeah, because cosine of 0 is equal to 1. So this at x is equal to 0 has to be equal to 0. Well, if you plug in for the sine term, obviously sine of 0 is 0, so this term vanishes. Cosine of 0 is always 1. So if this whole thing has to be equal to 0 for x equals 0, that implies that b is equal to 0. So that gets rid of one of our constants of integration, so we're just left with this equation here. Psi is equal to a times sine of kx. Now for the right-hand side, again, we have psi at I cannot speak today. Psi at x is equal to L is equal to 0. That implies that k is equal to n pi over L. Since a is not going to be 0, this sine term has to go to 0, and that implies basically that this argument is some multiple of 180 degrees, right? So n is going to be equal to 1, 2, 3, and so on. Basically a whole positive integer, not equal to 0, since again 0 would set this whole thing equal to 0, and then our constraint about the integral of the square equals to 1 would be broken. So 0 is not allowed, 1, 2, 3, 4 is fine. So that basically just gives us our eigenvalues here. So just back substituting in, we can solve for e, and I'm going to write this as e sub n now because it's a function. It depends on the value of n, be it 1, 2, 3, 4. So this is these are our energy terms here, and now we have to figure out the constant a, and we could do that again by our normalization condition. The integral between 0 and L of this, the square of the square of our wave function has to be equal to 1. Let me write some parentheses around this kx here so it's not as confusing. Yeah, that looks a little better. So the square of this integral is equal to 1. We just do the integration, we solve, we do a bunch of algebra, and we get a is equal to the square root of 2 over L. So this is our final answer for the actual wave function. Psi of x is equal to this again, with n equal to 1, 2, and 3. So let me write out a quick Python function to plot this for various values of n, and also print out the energy term here. So let me just shut off the recording and do that really quickly. Okay, for the inputs, or for the imports, all we need is numpy, matplotlib of course, and our solve IVP initial value problem solver. So down here I just wrote a function that takes some inputs, the mass of the electron in this case, h bar, the size of our box L, and n, that quantum number that we're going to increment, and this just basically returns the formulas that we just derived above, plots them out, and also prints out the corresponding energy here. So down here again, mass of the electron in kilograms, Planck's constant, h bar, Planck's constant divided by 2 pi, and I'm going to set L equal to 5 angstrom, so 5 times 10 to the minus 10 meters. So let's just do a plot. Oops, what's going on here? Plot eigenfunctions, m, h bar, L, and let's do the first quantum number 1. So this is what our first wave function actually looks like here. So just basically it's just half of a sine wave. The energy right here in joules is basically 2.4 times 10 to the minus 19. Let's increment this to quantum number 2. So we have a little bit more, we have kind of a full oscillation of our sine wave here. Our energy here is now almost 10 to the minus 18. It's 9.6-ish times 10 to the minus 19. Let's just do quantum number 3, unless so we're not here all day just counting these things. Now we're up to 2.2-ish times 10 to the minus 18, and we have more oscillations here. And as you can see, as we go to higher and higher quantum numbers, we're going to get more and more oscillations of our wave function. So that's the analytical solution, and now let's work on how we might do the numerical solution. So down here, let's just make this a markdown cell and say numerical solution. And again, this is via the shooting method. And for the shooting method, we need to use the initial value solver, which we pulled in with our imports. That's the solve IVP function, and that takes a function as one of its arguments. So in this case, it's going to be our differential equation, our Schrodinger equation here, the spatial variable x, the wave function variables I called y here, and I'm going to pass in the energy as an additional parameter. And for whatever reason, I hard-coded the mass and h bar into the function directly rather than passing them in as parameters. So again, this is a second order differential equation, and you need the solve IVP only does first order equations. So we transform our second order into a system of two first order equations. We've done all of this before. It's pretty straightforward. So let me just run the cell so we have our function. And now I'm just going to kind of manually go through the shooting method for this because we've done it in previous videos, so I don't want to spend a lot of time here. So let me set that up. So this is going to be our spatial variable x. It goes from 0 to L, and I'm just going to have 1,000 steps just for plotting purposes and to make things clear. And the x span, which the solver requires, is just going to be the first and last elements of that vector. So now I'm going to pick a value for my energy. This is the value we're going to adjust for our shooting method, and I'm just going to pick it to be 1 times 10 to the minus 20. And now let's set up the rest of our solver here. Since we're using an initial value problem solver, we have to pick our initial value. So I'm going to set those to equal to y0, and that's going to be equal to a vector at x is equal to 0. We know what that wave function is. It's 0, but we don't know the derivative of that wave function. So I'm just going to pick an arbitrary number. Let's just call it 1. And I'm going to justify this kind of after the fact. So I'm going to go through the process of solving it and then talk about why we can just kind of choose an arbitrary derivative value for the first derivative. So now I think we're good to solve. So let's go, our solution is equal to solve IVP. Our function was called equations, I believe. Well, actually, since we have to pass in this additional parameter e here, we can't just send in equations because there's a bug in, I don't know if it's a bug or they changed the way solve IVP works. You cannot pass in additional arguments. So what we have to do instead is kind of just use a lambda here. So we're going to do lambda xy is equal to equation xy and our value e, which is set here. Okay, and now we need to pass in our x span, our initial values, and we want the output at our x vector. So t eval is going to be equal to x. That should run. It seems to. Let's plot the results now. So for convenience, I'm going to pull out our solution psi here and just do a plt.plot x comma psi and make it a black line. Well, that's not what we expect. We expect it to go up to some value and then come down and be 0 at x is equal to 5 angstroms. So we need to adjust our value of energy. So let's go higher. Let's go 1 times 10 to the minus 19. What do we get now? Well, that's better. It kind of goes up, but we need to go probably pretty higher. Let's go 10 to the minus 18. Okay, that overshoots, obviously. That's almost good for like the second mode of this problem. So let's go 5 times 10 to the minus 19. Okay, better still. 3, 2, 1, go. So let's turn on some grid lines here to make this a little easier to see. PLT dot grid, not P grid. And you can kind of see how this is going to go. We're just going to keep tweaking this. 2.5. It's pretty good. So we need to go, it's too much curvature, so we need to lower it a little bit. 2.2. 2.3. 2.35. And so on. You see where this is going to go. Let's go to 2. Did we do 2.4? 2.4? 2.4 is almost perfect. What was our number that we calculated up here? That's 2 oscillations. Where's 1 oscillation? Oh, that's right. We hard-coded this in. So our actual energy is 2.3914, and we're damn close at 3. Yeah, okay, so we're good. 39. Perfect. So now the issue is, why can we just arbitrarily choose a value of our first derivative of psi? So I'm going to write this up better afterwards, but let me just kind of do it down here in a kind of a half-ass way to explain it. So here's our Schrodinger equation. Here, if psi is the solution to this equation, it doesn't have to be physically a normalized solution, but as long as we satisfy this differential equation, then a, some constant a, excuse me, times psi is also a solution. And you can see that pretty intuitively. If you plug in a times psi in here, it's just going to divide out because, you know, the linear nature of differentiation. So this would be a h bar squared over 2m times a times the second derivative of psi, and then we have a here, and they just divide out. So, but then again, that just makes the first derivative of our new solution. What is that? So pretty obviously, if I differentiate a times psi, I just get back a times the first derivative of psi. So basically, when I plug in some arbitrary value for this that happens to satisfy our boundary conditions, like this one does, all I'm doing is getting back some scaled a times psi of the solution we actually want. So to get our final solution, now that we have the energy, all we need to do is normalize this by our normalization constraint, which is up here. I wrote it. Well, that's it for the the analytical solution. We just have to do it basically numerically now and divide through. So let's just kind of come down here again and normalize this to get our actual function. So we need the area under basically psi squared. So let us do this. Let's say area is equal to trap z, np dot trap z. The variable, the function that we want to integrate is psi squared, and we're integrating with respect to x. And then we need to divide the numerical solution, psi is equal to psi, divided by, this is the area squared, so the square root of that, np dot sqrt area, and that should do it. So we get a function here, our boundary values are already right, we know that, and we got a function that peaks at a little over 60,000. What do we get up here? A little over 60,000. So let us do this one more time for the second energy level. So that's our what the wave function looks like for the second energy level, and we just repeat the process again. So let's go to, I don't know what the energy is. I should have looked at the number above, 4. That's obviously too small. 8, getting closer. 10, that's a little overkill. So it's 9, probably 9 point something. 9 is probably, I don't know, 9.1, 9.2. What do we get up here? 9.5. So, you just keep getting this until you get whatever precision you want. So 9 times 5, that's fairly close. We could get a little bit better if we wanted. And this function kind of has a maximum, again, a little above 60,000, and this one a little above 60,000. Awesome. So that is it. Yeah, so I am going to clean up this notebook and kind of write this part up better, why we can kind of choose arbitrary first derivatives. And yeah, this video is running longer than I intended. I was hoping to keep this about 10 minutes, and we're obviously probably double that. So I am not going to bother with an outro, and I will see you later.